Yeah, thank you very much, Kai, for your nice words, and thank you very much to Yuka and Ivan and the organizers for getting me so far to the north. As Kai said, I will tell you about certain aspects of stochastic thermodynamics, and I have packaged them under the title of current fluctuations. We have recently found that those are in an interesting way constrained by the entropy production, and that has impact on the precision of certain processes at finite temperature. And the catchphrase for that is that I will tell you about the cost of precision. Now, the basic idea of stochastic thermodynamics is kind of shown here in this cartoon. You all know that 200 years ago people wanted to understand the rules by which you can transform the various forms of energy, heat into mechanical work and vice versa. And this is what classical thermodynamics is about. And about 20 years ago people started to wonder whether these rules, which have been developed here, can be applied to much smaller systems like this enzyme, which is the F1 ATPase, the smallest rotary machine, whether these rules can be applied and how they can be applied. And another important class of systems is transport here, for instance, through quantum dot, my cartoon version of it, which has to do with thermoelectrics, which is one of the fields studied here in Helsinki very, very intensely. Now, before I tell you about the crucial role of fluctuations, let me first talk about currents. And I've chosen here an example our chairman was involved with when he was still in Stuttgart. So I will show you here a system which is based on the Nernst Effect, which in a sense hopefully fits to what we've heard this morning. So as you know, the Nernst Effect, the idea is that a heat current from hot to cold drives a perpendicular particle current uphill an electrochemical potential. And the key idea or the key point is that this coupling works only in the presence of a magnetic field. So what we did in this work, this was the master thesis of Julian Stark, supervised by Kai Brandner in my group. What we did is that we tried to come up with the arguably simplest microscopic model for such an effect. So in order to have this heat current, we have a hot bath, a cold bath. We model each reservoir as an ideal gas. And when particles leave the reservoir and enter the central scattering region, they just follow Newtonian dynamics. They have charge, so they go through these Lorentz cycles. And we choose the chemical potentials, i.e. the concentrations and the four temperatures, such that at the end of the day we only have a net heat current uphill, no particle current, which then drives this perpendicular particle current uphill a chemical potential, but all mu's and t's are chosen such that there is no net heat current. Okay, now this is a problem which you can in principle solve almost analytically under the assumption that these are ideal gases and that you have fully transparent boundaries, i.e. whenever a particle leaves here, it will just undergo Hamilton's motion and then enter the corresponding reservoir. Now in such a system you can easily calculate the currents, and then you can define an efficiency which would be the output. That's the current, that's what you want. You want to drive particles uphill the chemical potential, and the input is the heat current. And when you do the numerics as a function of the magnetic field, you get for that efficiency in units of the Carnot efficiency, you get plots like this. This is now as a function of the base concentration or temperature. This is as a function of the aspect ratio, i.e. the relative proportion of these heat segments versus the particle segments. But the key point is that the efficiency goes up with increasing magnetic field, but even when you crank up the field enormously, you find that the efficiency reaches a kind of top value of about 17% of the Carnot value. The question is, where does that come from? And it turns out that this is one incarnation of a more general bound, which Kai actually investigated during his PhD, where he looked into kind of n multi-terminal model using a Landau-Büttiger approach for scattering between the different terminals. At the end of the day, two of them can be singled out as real terminals with certain chemical potential and temperature, and the yellow ones serve as what is called probe terminals, which somehow mimic inelastic events. And it turns out that current conservation implies, and that holds for quantum as well as for classical mechanics, implies a constraint on the Onsager, the effective Onsager coefficients for that transport. So you have particle-particle Onsager coefficient and heat-heat Onsager coefficient, and you have non-diagonal Onsager coefficients. Now usually they are symmetric, but when you have a magnetic field, that magnetic field breaks time reversal invariance, and therefore LPQ doesn't have to be LQP. So you have a new variable, which is this ratio of the non-diagonal Onsager coefficients, which would be 1 in the time reversible situation. And the universal result is that as a function of the number of terminals, there is a constraint on these Onsager coefficients. And this constraint on the Onsager coefficient translates into a constraint on the maximal efficiency, which is shown here as a function of the number of terminals. So the lowest curve is for 3 terminals. 4 terminals is this curve. And in this Nernst geometry, due to symmetries, this ratio of the non-diagonal Onsager coefficients is at -1. And then you can just read off from this analytically known curve that the maximum efficiency is bounded by 17%. Whatever you do, you can't do better in such a 4-terminal geometry. And in order to reach Carnot efficiency at x values which are larger than, absolute value larger than 1, you would have to go to an infinite number of terminals, and even then you would not reach finite power, which was one of the original speculations in this field by Casati and Benenti in 2012. Okay, so these are just currents. There's no fluctuations yet. And this is linear irreversible thermodynamics. But I want to talk about, in the main part now, about current fluctuations. And therefore, I have to tell you a little bit more about this idea of stochastic thermodynamics. And let me first point out that it's a quite comprehensive general framework which applies whenever the non-equilibrium is caused by mechanical or chemical forces. This would be mechanical unfolding of a protein. These systems I've talked about. However, and that's key, you still need the notion of temperature. So your non-equilibrium, your driven system has to be coupled to a heat bath of well-defined temperature. In all our bodies, for instance, we are deeply in non-equilibrium. All our cells are in non-equilibrium. Still, temperature is very well-defined, 37 degrees. And obviously, because we're dealing with small systems or a small number of involved molecules, fluctuations are important. And the key idea is really to take thermodynamics seriously, not only on an average or bulk level, but you can take energy conservation and even entropy production, as I will show you, seriously along individual stochastic trajectories. And if you want to get a more comprehensive picture, you will find 600 references in this review. So how does it work? My favorite paradigm is actually a colloidal system. So suppose you have a colloidal particle which you can manipulate by optical tweezers. So for instance, you can create a periodic potential by tweezers, and then on addition, force that particle along this potential by a non-conservative force. Now, typically in the time scales accessible to the experiments, the motion is overdamped, so there's a Langevin equation. Velocity is given by the mobility times the total force, which has 2 contributions, gradient of a potential, this non-conservative part. In addition, there is the thermal noise from the aqueous solution, which we keep in the usual Einstein delta correlated form, related via temperature to the mobility. Now, the system is under non-equilibrium conditions because there is this non-conservative force or because the potential is time-dependent through some external driving. Langevin equation has been around for 100 years, It was only about 20 years ago when Ken Sekimoto pointed out that you can cast this Langevin equation in the form of the first law if you identify the terms properly. For instance, when you change the strength of the potential, this is an external work like lifting the particle, or non-conservative force times displacement is external work. Internal energy is just position within the potential, and then this blue box, the first law, works out if you identify the heat as the difference, and that turns out to be the total force times the displacement. Maybe this is something you would have guessed anyways. That's just friction. Now the key point is all these quantities are fluctuating quantities along the trajectory of such a particle. Look at my green dot. This is a fluctuating trajectory. All this is defined along this fluctuating trajectory. Hence, heat is fluctuating, and you know that heat is related to the entropy change of the surrounding medium via this relation. So we have here a fluctuating contribution to entropy. Now it turns out that there is a second contribution to the entropy production. Not just the medium, but also the system proper has an entropy which you get by looking at the increment of the log P. P is the solution of the corresponding Fokker-Planck equation. This is a little bit brief perhaps, but at the end of the day you can prove that when you look at the total entropy change along a fluctuating trajectory, you put that in the exponent, you average over arbitrary initial condition. You don't have to start in thermal equilibrium over an arbitrary time interval, arbitrary driving. You always get 1 for that exponential average, from which you get this second law-like statement by Jensen's inequality. Okay, so these are, of course, lots of equations. So let me show you that it really works also with experiments. So this was the first experiment using non-harmonic driven potentials almost 10 years ago with Clemens Bechinger in Stuttgart. We did that. So the idea is you have a particle in this kind of potential. There's a repulsive wall. It's a colloidal particle. This is distance to the wall. And the linear attractive part you create by a laser field, and by changing the amplitude of that laser field, you can change the slope of this potential, which you can then vary in a sinusoidal fashion. And then by measuring the distance very carefully, you can infer all these quantities I had on the previous slide. And then as a function of the oscillation number, for instance, the black curve is the work. So you see typically you put in about 5 kBt per oscillation. You take out, heat is dissipated, this work is dissipated mostly as heat, same order of magnitude. There is a little bit of a change that the green curve, which you can hardly see, in the internal energy. And for any pulse, any oscillation, if you add up the 3 colors, you should get 0. Here is the histogram of the error. So you see, with this kind of experiments, we can identify heat, work, internal energy with a precision of about half a kBt. You can also look at the distribution. Suppose you do that for 20 oscillations. You get this kind of work distributions. You see by naked eye that this is a non-Gaussian curve. Gray is the data, red is theory, no fit. Here is 0, by the way, so you have even events here where you put in no work on average. And it turns out that this work distribution for such a symmetric driving has to obey what is called a detailed fluctuation theorem. So there is a symmetry on this distribution. And this is just one relation, as was the previous one on the integral fluctuation theorem for entropy production, one of these exact relations which started with the Jarzynski and the Crookes relation. Okay, so I will talk about current fluctuations today, mostly, or I think exclusively, in non-equilibrium steady states. So for those, there is this famous fluctuation theorem first discovered by Evans and co-workers numerically in 2D sheared fluids, and then later generalized within various dynamical frameworks. Typically, it's a long time limit asymptotic statement. However, when you buy this identification of entropy of the system, it holds. It's easy to show that it holds in finite time. And it's important to have something which holds in finite time, because experimentally, at least in bio and colloidal systems, it's very hard to get to this long time limit. So here is, for instance, in this kind of situation, the red curve here is the total entropy production, the distribution after 2 seconds. This black curve is after 20 seconds. These are anything but non-Gaussian distributions, bimodal, trimodal, but they all, however they look, they have to obey this fluctuation theorem. So in a sense, of course, that's an old story. Now I want to show you what happens if you have slow degrees of freedom which are not accessible to the experimentalist. So that's now the role of hidden degrees of freedom and the fluctuation theorem. This is something we investigated again with Clemens Bechinger a couple of years ago. And the idea was the following. Suppose we take 2 of these colloidal particles, each has its own potential, each is driven along this potential landscape, and we now make the particles paramagnetic, so viewed from top, it's this setup, and in the presence of a magnetic field, there is some dipolar interaction between these 2 particles. Now, no doubt, if you look at the combined system, this is a genuine non-equilibrium steady state which will obey all the exact statements of the theory. However, suppose you have this kind of system, but you can observe for whatever reason only one of the particles. And suppose that you do not know that there is another one. So suppose x2 is hidden. If you then apply the rules for calculating the total entropy production, you would come up with what you could call an apparent entropy production. And the question now is whether this apparent entropy production still obeys the exact result, still obeys the fluctuation theorem. And here are the data. Now the nice thing, of course, about this system is that you can tune the coupling by tuning the magnetic field. So here is this probability distribution for the apparent entropy production. The red curve is with coupling, the black curve is without coupling. So you see in both cases, when you plot it logarithmically, that ratio, you get a slope, but the slope changes. So here is how the slope changes as a function of the coupling. With increasing coupling, the slope goes down. Even worse, perhaps, the slope also becomes time dependent. So the longer you allocate data, the more the slope goes down in the case where there is a coupling. Now I should say that, of course, I was not expecting them to find a slope. I was actually expecting to find just some asymmetric curve, but they had to work hard in the experiments, and we did simulations. We also had to work hard there to find deviations from this kind of linear behavior. Now we will come back to this. I will tell you the physics or the explanation behind this in a minute, but I want first to describe a similar phenomenon for another system. And in order to do so, I have to introduce that concept of affinity of cyclic enzymes. So let's go back to this F1 ATPase. This is a molecule which is membrane bound, and typically in our cells it's driven by proton gradients across the membrane, and it generates ATP. ATP is the basic fuel for all biomolecular processes. However, if you isolate that lower part, you can provide ATP in excess. Basically, the thing rotates. One subunit of this molecule rotates. So with each hydrolysis step, it moves 120 degrees. So after 3 steps, it's back at the original position. And when you reach back to an original position, you go through a cycle. And what I want to define here is the affinity of a cycle, which is the delta mu associated with the chemical reactions. That would be the input. And if you let it run against an external force times distance is mechanical work, that would be the output. Now the key point is that when you come up with the kinetic model, you have to make sure that the logarithmic ratio of these rates obeys this affinity. So for instance, if you have no affinity, i.e. no driving force, you have to make sure that K plus and K minus is the same. Otherwise you would get motion without any input. You would actually violate the second law. Now this affinity is important because the total entropy production is given by the sum over all currents times all affinities. And in such a simple model, which is just an asymmetric random walk, you get this. And you can, of course, the entropy production identify with the work which you get out, or the rate, the power which you get out, minus what you put in. Yes, that's correct. And then, of course, the efficiency would just be the ratio, again bounded by 1. Now, this is a simple example, but you can come up, or you can generalize this. You just have a number of states. You have transitions. You have transitions where you put something in, like chemical energy, and you have transitions where you get something out, like force times displacement, when you let your system run against some mechanical force. Okay, so here are real data for this molecule. There's one more point which brings me back to this issue of hidden degrees of freedom. This molecule is really small, so you put that part on a cover slip, you provide ATP in excess, and then this purple gamma unit turns around. But this is too small, you can't see that. And in order to see that, you have to attach a big dumbbell-like sphere, no, dumbbell to it, I should say, and then you can see that optically. So this is like the digit of a watch. You can see then how the angle changes as a function of time. And when you look at this blue trace, you see a clear 120 degree steps in this motion of this big dumbbell-like object. Now, if you provide more ATP, the whole thing is running faster. This is the red curve. Then it looks a little bit more continuous, but there are still fluctuations. And then, of course, one of the issues is how do you relate that kinetic to the thermodynamics? What about first law? What about efficiency in terms of a machine? Now, this efficiency is not something I want to address today, but I want to go back to this issue of the fluctuation theorem. But let me first show you how you can model that. And this makes clear the essential role of a hidden degree of freedom. So first we map that rotary motion to a linear motion. Now, this purple subunit, that's this little motor. And this does discrete 120 degree steps. And each step comes with a hydrolysis, one chemical reaction. Now, when the motor jumps forward, it is loading that elastic spring between the motor and this probe particle. This is what you see in the experiment. So you have 2 degrees of freedom, which are coupled. This one you can see, and this one you don't see. For this one, you take the Langevin equation. For this motor, you use one of the thermally consistent master type equation dynamics. So the ratio of forward and backward rate involves the chemical potential and the loaded elastic energy of that spring. Now this you can put easily on the computer, and then you get trajectories like the one we've seen in the experiment for different concentrations of the fuel. The more fuel you provide, the faster it runs. And the nice thing is here that we can see the motor steps, which are these discrete steps, and we see the fluctuations of the probe particle around it. So here you see that the motor steps, and then the beat follows and fluctuates again. But sometimes, like here, the motor steps, the beat doesn't follow, the motor has to be pulled back, and then tries again, and the beat finally follows. So when you look at in the stationary state, you can look at the average distance between probe and beat, and you get this kind of curves which develop this shoulder. If the motor runs faster, it can be typically 1 step ahead, which is this second peak which here develops. Now for this molecule in such a setup, the Japanese Nojis group, they looked at the fluctuation theorem. So they plotted the angle, the increase in the angle as a function. I mean, for a fixed time, you get this kind of distribution. Each color is a different time. And then again, they plot that ratio logarithmically as it is appropriate for the fluctuation theorem, and they found a slope. And the idea was to extract from this slope the torque which is driving this rotary motion. So if you forget about hidden degrees of freedom, you would just write a rotational Langevin equation for the angle, and then by looking at that slope, you could infer the torque without knowing the friction coefficient, because that's hard in this geometry where you're close to a cover slip and so on. Now the problem was, and this relates back to what we found with Clemens Bechinger in our system, the problem was that this torque became time dependent, i.e. the slope here is time dependent. And this time dependence again is a signature, as we now know, of the fact that you have a hidden slow degree of freedom. Now they thought they could infer the torque from the t to infinity limit, which turns out actually to be wrong. So let me show you what we get in our simulation. So these are our data, look very much like the experiments. We look at the slope as a function of the time, and exactly the same behavior. The slope goes down as a function of time, but we can now show that you should infer the torque from the t to 0 limit and not from the t to infinity limit. However, in this study, we found something which has broader implications. When you now look at the long time limit of this motion and you go through this generating function, so I think I can be brief here. We're looking at the large deviation function of the probability of that beat to have traveled a certain distance. Then we found this modulation here. So when you plot that probability for large times as a function of the distance around 0, which is around what you would do for the fluctuation theorem, you indeed find a kind of modulated behavior. Now, you can easily then show, going through that formalism, that there is a discrete symmetry of that probability distribution. So if you go 1 unit along the track, you get this exponential suppression, i.e. when you look at the logarithmic ratio of the distribution, you get a slope plus an additional function. And this has an important implication. It means, for instance, that the slope at 0, that's what people would usually plot, the slope at 0 has nothing to do with entropy production. What you have to do is you have to look at the kind of discrete slope, which is the green line, and that tells you, that determines the entropy production. Now, this is a general phenomenon when you look at such probability distributions. So here is the rate function. This is usually in a linear problem that would be a parabola. Here is the maximum. That's the average velocity around the average velocity. Here is that kink where you look for the fluctuation theorem around 0. But our prediction now is when you zoom in such a plot where you plot that rate function, you would always see these oscillations, even here on the top. In any model where you have spatial periodicity and hidden degrees of freedom, you should get this kind of fine structure. And this is a prediction which has not been yet verified in experiments, but we think that this would be a quite general statement. Okay, now let me come to this issue which I promised on the cost of precision, which also has to do, as you will see, with current fluctuations. And I want to introduce this by recalling a simple system which you all know, which again is the asymmetric random walk. But I want you to look at this as a process. So suppose I call this a process and the number of steps is the output. So the number of steps I make is the output of that process. So whenever the two rates are non-equal, there is on average, there is such an output. But this output is not sharp. After a certain time, I have not always made 10 steps. I may have made 11. I may have made 9. So that comes with a certain variance, which is the diffusion coefficient, which, of course, as you all know, is the sum of these two rates. But now I define the key quantity. The key quantity is the precision or the uncertainty of that process, which is the variance divided by the mean squared. which is this expression. Now, I told you that in any thermodynamically consistent setting, I have to drive the system in order to break the symmetries. And this involves the thermodynamic cost. So suppose with each forward step I hydrolyze an ATP. So the cost is the current times the affinity times the time. The affinity is what I just had. This is this change in the chemical potentials. Now you combine everything and then you find a surprising relation. You find that the cost for this process times its uncertainty squared is given by this function, which is bounded by 2 kBt. So for the simple asymmetric random walk, there is a relation between the precision and the cost. Now, how general is this? Suppose you have a general unicyclic process. So going through that cycle of 6 different states, I always produce 1 unit after going through these 6 states. So you can easily show that we have the same relation except for the fact that we now have to divide the total affinity, which is the logarithmic product of all forward rates divided by all backward rates, by the number of states. Again, this is bounded by 2 kBt and both bounds are sharp. First one saturates if you have all forwards rate the same, all backward rates the same. Second bound saturates close to equilibrium, i.e. in the linear response regime. And this is, I think, now really remarkable, this inequality is even true for a general, arbitrary, multicyclic Markov process. So even when you have internal cycles, if you had some more involved model of the internal states of a motor, whatever you do, the claim is you cannot beat that bound. If you want to have a very precise process in the sense that after a certain time you have a very sharp outcome, you have to pay lots of free energy to have this machine running. So for instance, a precision of 1% inevitably costs at least 20,000 kBt. Whatever you do, you can't beat that. The reason is why this holds even for multicyclic processes, that by adding cycles to a unicyclic process basically increases the fluctuations and you do not really gain precision. You pay more and you don't gain precision. So I should say that we have proven it in certain limiting cases. We did lots of numerics. The full mathematical proof was then just found a year later by the MIT group. So now it's a theorem. And as you can easily imagine, this has, of course, important consequences. I want to show you one consequence which we have explored, which comes again from enzyme kinetics. Suppose you have an enzyme can bound a substrate, and then the substrate will transform into a product, and then the product will be released. So if you just had this upper triangle of 3 states, this is what is called Michaelis-Menten kinetics. But suppose this enzyme can bind 2 substrates, and then it can transform the first to product, the second one to product, and then go back. Then this is a more complicated reaction scheme. Suppose as an experimentalist you can measure the fluctuations, and now I'm using the Fano factor where you look at the variance divided by the mean. Then our previous results imply that this Fano factor, i.e. the fluctuations of the output, are bounded by this function, where A is again the affinity involved in one of these reaction cycles. And it turns out that this Fano factor is bounded by this function, where Mmax is that cycle which has the largest ratio between number of states divided by number of products. So for this upper cycle, this is 3 states, 1 product, so that ratio is 3. For the big cycle, it's 6 divided by 2, which is also 3. But if you take the blue cycle here, you have 5 states and you transform only 1 product. So suppose you measure a Fano factor of 1/2. Suppose you know the affinity of the chemical reaction. Then this relation tells you that the Mmax has to be larger than 3, which means that the simple Michaelis-Menten scheme is not possible. So you can now use measurements of the fluctuations as a diagnostic tool to infer unknown properties of the underlying network, of the underlying chemical reaction network. This again is a very general idea which we have exemplified here in this particular example, and I would expect more of such, in a sense, practical applications of these universal relations constraining the fluctuations to show up in the future. This is now all based on looking at the second moment. More recently, we have even found more general bounds. So this is basically a reminder on what I just told you. This is this asymmetric random walk. We're looking at this rate function. Here is this rate function for different affinities. So if affinity is close to 0, then you're close to linear response, then it's just a parabola. But the more asymmetric that random walk is, the more asymmetric looks this rate function. And what I've just introduced, this uncertainty relation, basically is a relation around the curvature here, which if expressed in terms of this rate function means that the second derivative has to be less than the entropy production sigma over 2. Now it turns out that, I mean, you can see it by naked eye, that here all these colored rate functions are bounded from above by a parabola. Now it turns out that such a bound, again, is globally valid. We've found that any current, whatever current you look at, any current in any network can be bounded, or the extreme fluctuations of that current can be bounded by the entropy production. So here is the general statement. The large deviation function of any current is bounded by a parabola which involves as curvature the entropy production. Or if you go to the cumulant generating function, which is the Legendre transformation, you have this kind of statement. So here are again data for various networks with various number of vertices. Again, this was proven, it was conjectured by us, it was proven in this paper. So we have now general bounds for any current in any network. Entropy production determines or provides a bound on the fluctuations. Now, if you know a little bit more about your network, if you know in addition the affinities of the different cycles, we have even more refined bounds which involve the number of states, the affinities. I don't want to go into this. You'll find it in the preprint. But I think it's an exciting development to find general bounds on such extreme fluctuations. Okay, so in the last 5 minutes of my talk.
Presumably 10, we started 5 minutes later.
Okay, good. Well, okay, that's perfect. That will be fine. I want to show you again another aspect of this non-equilibrium stochastic thermodynamics, how it relates to a, again, concept which is used in different fields, and that will be work which we have done with Felix Ritter, where we're looking at what is called the effective temperature in non-equilibrium steady states. But in order to introduce this, this will be my last theory slide. I have to remind you on the fluctuation dissipation theorem. You all should know the left-hand side. So in equilibrium, you know that if you have a system which you perturb by a field F, and you look at the response of an observable A at time t2 to a perturbation, the response to a perturbation F, which was applied earlier, well, the FDT tells you that you don't have to look at this response function, you just look at the corresponding equilibrium correlation function. And the nice thing about that FDT is it's true for any observable A, any time difference, i.e. any frequency in the frequency domain. And the physics behind it was Onsager's insight. Onsager realized that the decay of a fluctuation is the same whether that fluctuation was generated spontaneously or by an external perturbation. That's Onsager's regression hypothesis, which is formalized in this theorem. Now suppose you have one of these non-equilibrium steady states where the system is driven. You can ask the same question. Suppose in such a NES, I'm looking at the response of an observable A when I perturb the system by a force F at an earlier time. Can I still write the response function as the corresponding correlation function? Of course, now I would have to take that correlation in the non-equilibrium steady state. Well, if that's possible, at the price of a modification of that temperature, if that's possible, then this is called an effective temperature. And of course, in general, you don't expect that to be true. You don't expect that. You can, of course, always write it in this form, but then the effective temperature would depend on the observer, and it would depend on the time difference, i.e. the frequency. So it makes sense only if you have that over a certain frequency range. And this is something we wanted to explore in single molecules. This is a study with my PhD student Eckhard Dieterich, and these are two students and a postdoc in Felix Ritor's group, and this was published just last year. So the idea is the following one. So suppose, before I tell you about the molecule, let's take a colloidal particle in a trap, in a colloidal trap, and we apply a force, a dichotomous force to that particle. So the particle is subject to this kind of binary force where the switching is just random. And that, of course, then generates a nice non-equilibrium steady state. In such a non-equilibrium steady state, we can measure the position correlation function. But in this NES, we can also now apply an additional force and look at the response. And this is now integrated response. That's why I call it chi. Okay, so we have these two functions, and now you can plot them parametrically. And then there are two cases. Either you find that the response versus correlation is linear, in which case you would call that slope an effective temperature, or in such a parametric plot, it's not linear, and then there is no effective temperature. So we first studied exactly that colloidal part in a trap, which is a harmonic oscillator. And there, of course, it's nice. You can do everything analytically, also Langevin equations. So here is this non-equilibrium steady state. You switch the force. You apply a perturbation. Here is the response function for different parameters. Here is the correlation function. You plot it parametrically. In the red and the blue case, you find nice slopes, i.e. you find nice effective temperatures. In the green case, you don't find such a regime. What is the physics? The physics is that this additional force, if that changes on a very short time scale, it acts like additional thermal noise. So whenever that frequency here is high, or that relaxation time, not the relaxation time, that time over which the force changes, if that is significantly smaller than the system relaxation time, then you have an effective temperature, otherwise not. So you can have this kind of phase diagram, and when you have an effective temperature, you can calculate its value, for instance, using this Langevin equation. Of course, we were really interested not in harmonic oscillators, but in DNA molecules. So here is a short DNA hairpin with tweezers. That's how the experiment is done. And for a short hairpin, this hairpin is either closed, folded, or open. So basically, we have a four-state system. We switch the force between two values, and then the molecule switches between two values. So in that force extension space, basically you go through this kind of loop. So again, that's a current in this space. If you plot the histogram, you get this kind of diagram. So it's a four-state system. You can have it folded and the force applied, unfolded, force applied, and the same thing here with no force applied. We're measuring response and correlations. We plot it parametrically. Again, for a system which by itself would slowly hop between these two states, we find through this additional excitation an effective temperature, which turns about a factor of 2. However, if the molecule is faster than this external excitation, this whole concept of effective temperature doesn't make sense. And finally, and this is my last slide, finally you can do that even for a long DNA molecule which has the rough landscape. I mean, this was Felix's original motivation to look into this. There, of course, it's a little bit harder with the data, but still you find conditions where you have a nice slope here. However, you get pretty large values for this effective temperature. Okay, so that's basically what I wanted to show you. I have introduced that framework as a quantitative one for these kind of processes, and then I don't want to read through that list, but I want to highlight again the people here who did the work. Thank you for your attention.